Hello there, Mr. Sutton here, bringing you the Algebra 2 6-1 Part 2 homework solutions on exponential growth and decay. In this one we're focusing on writing exponential functions. For this problem we have the value of a mountain bike given by this y equals 200 times 0.65 to the t formula, and t is the number of years since the bike was purchased. Y is in dollars. So they have a few tasks for us, the first of which is determining whether the model represents exponential growth or decay. And to answer that question, we're just going to look at this b value here. This is in the form of a times b to the t. The b value is between 0 and 1. That tells us that this is going to be decay because we keep multiplying by a number that's less than 1 and greater than 0. So that's decay. Now for the annual percent increase or decrease in the value, we're going to rewrite this b value as a 1 minus r sort of setup. That's going to put this in decay form. So I can write this as 1 minus, let me think, 0.35. That means that we are losing 35% every single year. And now they also want us to estimate when the value of the bike is $50. Well, we have a formula for the value of the bike. It's this y equals formula right here. If we want that to be $50, we need to replace y with 50 and then go ahead and solve for t. Now we're going to do this on Desmos at this point. So here I am on Desmos, and let me graph both sides of this equation down here. So I'm going to do y equals 50, and I can't see that because that's way up there. I'm going to have to zoom out in a minute. Let me also do y equals 200 times 0.65. All of that raised to the, I'm going to make it x because I haven't defined any functions in terms of t on Desmos yet. And then I see a little piece of that exponential function. Let me zoom out and see where that intersects the 50 line. So if we go up a bit, zoom out, there it is, right up there. So the intersection point is 3.22-ish. So then at time 3.22 years, that is when our bike reaches a value of about $50. On this one, we're told that in 2012, there's about 6.26 billion cell phone subscribers in the world. And during the next 5 years, that increased by about 4% a year. All right, well, we'll take their word for it. That seems a little high, but whatever. They want us to write an exponential model that represents the number of cell phone subscribers t years after 2012, and then estimate how many subscribers there are in 2016. All right, so we have to pick a model here. We either want to go with a growth or decay form, and I'm thinking since the number of cell phone users is increasing, we should go with our growth form. So a times 1 minus r to the t. This will be our formula here. So we've got the a value, that's the initial starting amount. So at time 0, which is actually 2012, we started with 6.26 billion subscribers. And this is all expressed in billions, so we can just write 6.26 right there for the a value. For the r value, we are increasing by 4%, so I'm going to write 1 plus 0.04 because I have to use a decimal to express that. And then t is just kind of around for the ride here. So if I want to simplify this, my final formula for number of cell phone users is 6.26 times 1.04 to the t power. Now if I want to figure out the number of subscribers in 2016, that's 4 years after 2012, so I actually have to plug in 4 for this function that I just created here. So we've got 6.26 times 1.04 to the 4th power, and I'm going to need Desmos to evaluate this. So let me just create the function, and then I'll plug stuff into it. So our function originally, we had f of t equaling 6.26 times 1.04 to the t. There we go. And now I'll just do f of 4, and that'll take care of it for me. And that's going to be about 7.32. So 7.32 billion people have cell phones apparently in 2016. For the next part of the problem, they want to estimate when the number of cell phone subscribers was 7 billion. Well, we already surpassed that in 2016, So I'm guessing it's going to be somewhere before 2016 that we're looking for, and after 2012. So let's actually write an equation that we can solve for this. So here's my formula. F of t equals 6.26 times 1.04 to the t. If I want the output of this formula to be 7, exactly 7, I just need to set this equal to 7. And now I have an equation. I can go back to Desmos and solve. So back on Desmos, let me graph each side of this equation and then see where those two graphs intersect. This is the way to solve any equation. So we have y equals 7. That's pretty easy, just a horizontal line. And y equals 6.26 times 1.04 to the t. There's our exponential line. We see an intersection here. Let's just zoom out and make sure that's the only spot. I mean, we know it will be because exponential functions really only go one direction. They don't come back down. So let's see where that intersection is. It is at about 2.85 if we round that off. So here was our graph. We had t equals 2.85. Now they said estimate when. So if we want to give a fancier, more specific answer, maybe they're asking what year the subscribers was about 7 billion. This is roughly 3 if we round it off. But remember, t is number of years since 2012. So 3 years after 2012 is about 2015. For this problem, we're told that the cost of a swimsuit is increasing 8% every year. That must be some swimsuit. If the cost today is $35, what will the cost be in 10 years? So because we have a percent increase, we've got some exponential growth going on. So we're going to use our growth form, a times 1 plus r to the t power. And now if we want to know the cost in 10 years, we have to plug 10 into this function when we've assembled it. So f of 10 equals, the a value is our starting value. We started at $35. The r value is our percent increase here. So we've got 1 plus 0.08 if we turn that into a decimal. And again, since we're plugging in 10, this t value is going to be 10. So let's just evaluate this on Desmos to figure out the cost of a swimsuit. So we've got 35 times 1 plus 0.08, raise that to the 10th power, and that comes out to about $75.56. For this problem, we're told that the value of some industrial gear is decreasing by 10% every year. If the value today is 200,000, which is a lot, what will the value be in 6 years? All right, we have some exponential decay going on because we're decreasing that percentage. So we'll use our decay form, a times 1 minus r to the t power. If we want the value in 6 years, we're doing f of 6. The a value is the starting value, which was 200,000. R is going to be this 10% expressed as a decimal, so 1 minus 0.10 or 0.1. And we're raising that to the 6th power. Let's go to Desmos and plug all that in, clear out what was there before. So we've got 200,000 times 1 minus 0.1, raise that to the 6th power, and that's about 106,288.20 cents. For this problem, we're depositing $9,000 in an account that pays 1.46 annual interest, and we want the balance after 3 years when our interest is compounded quarterly. So since we're compounding more than once a year, not annually, we're going to have to use our compound interest formula. That's a equals p times 1 plus r over n to the nt. So for our p value, that's the principal, the starting amount, that's the 9,000 here. We've got 1 plus our interest rate, which expressed as a decimal is going to be 0.0146. And that's being divided by the number of compoundings we do each year. Since this is quarterly, that's 4 times a year, and that 4 gets used again in the exponent. And then finally, the t is our time of the investment, which is 3 years. So let's plug all this in Desmos. We've got 9,000 times 1 plus fraction 0.0146 all over 4. Close the parentheses. Let's raise that to the power of 4 times 3. And that comes out to about $9,402.21. On this one, they want the balance of an account earning compound interest, 2.29% compounded monthly, after 6 years with a principal of $3,500. Since we're compounding non-annually, we're going to use our interest formula here, P times 1 plus R over N to the NT. So for our principal this time around, we've got $3,500. And our interest rate is 2.29, so that's going to be 0.0229 if I plug that in as an R value. Our N, since we're compounding monthly, that's 12 times a year, and that gets used in the exponent again. And for the T, the time of the investment, that's this 6 years. So let's plug all that into Desmos. 3,500 parentheses 1 plus, and we have a fraction, 0.0229 all over 12. Raise that to the 12 times 6, and that all comes out to $4,014.98. For this problem, which is on the honor set, we're told that in a certain city the value of a house is increasing at a rate of 16% annually. They want the value of a $100,000 house in 4 years. Since we've got increasing going on, we can use our exponential growth form, a times 1 plus r to the t. The a value is the initial value of the house, which is 100. We're plugging in 4 to the f function eventually. So we've got f of 4 equals 100 times 1 plus the interest rate. So that's 16%. We're going to write 0.16 in there. And our t value, again, is going to be this 4 years that we're letting our house sit for. So let's go to Desmos and evaluate all this. So we've got 100,000 times 1 plus 0.16, raise that to the 4th power, and that's $181,063.94. For this one, we're trying to find the balance of an account that's earning compound interest, that's 1.83% compounded daily, after 6 years with a principal of $3,500. So since we're compounding non-annually, let's use our interest formula, P times 1 plus R over N to the NT power. Our principal is the $3,500. We have an interest rate of 1.83, so that's going to be 0.0183 if I use that as a decimal. Since N is the number of times we compound each year, and we're doing it, they said daily, that's going to be a 365 there. That's a lot. So that also goes for the N in the exponent. And the T is my 6 years for the investment. Let's plug all this into Desmos. So we have 3,500 parentheses 1 plus, let's do a fraction, 0.0183 all over 365. And let's close our parentheses and raise that to 365 times 6. That comes out to $3,906.18.